Good afternoon, everyone, and welcome to our second webinar in a series of webinars for the CCUS ZEN project. If you did join the last one, or if you haven't, it took place on the 23rd of April, which introduced the CCUS ZEN project. And there is a link to the recording on the event page of our website. I will add that to the chat, so you're welcome to access that later on. So today's webinar will be recorded. Will also be made available on the website. We feature two presentations today for you. You will have a chance to ask questions at the end. You will notice that apart from the chat function on Teams, there's also a separate Q&A section where you can submit text questions. So please use this for your questions. You can submit them at any time. We can go through them at the end. And if you prefer to speak your questions, you can use the hand raising function. When we get to the Q&A section, we can alternate between text questions and spoken ones, and we can enable the microphone at that stage for the audience. So our first presenter today, I'm very happy to introduce, will be Anne Lotta, who is research manager for the Reservoir and Geology Group at SINTEF. And she will then be followed by Betul Yildirim, who is an assistant professor at the Middle East Technical University in the Department of Petroleum and Natural Gas Engineering. So I'll now hand over to our first presenter. Anne, the floor is yours.
Thank you very much. I'm trying to share here first. Yes. Thank you very much. I'm very happy for be able to share some of the results from the CCUS project. The title of the presentation is High-Level CCUS Value Chain Screening. And this is, I will mainly focus on results from work package 1 in this project. So what is CCUS ZEN? CCUS ZEN is a Horizon Europe project, a coordination and support action under the coordination and support action going from over 3 years. And the aim is to enable faster development of CCS projects in industry clusters across Europe, and also come up with identifying potential projects for common interest. And also very important to share knowledge about CCUS for the industry, but also among the academics. And the project have many researchers work from the whole Europe working together, and you see that on the different logos. In addition, we have networking partners also that contributes in the meetings and are interested in the research. So we are very happy with that. And if you want to join as a network partner, you can contact either me or Eirik Falk da Silva, that is leading the project from SINTEF. Okay, so what do we work with? So in the project, in the CCUS project, we start out with a regional screening, doing a lot of technical mapping, but also non-technical mapping. So we look at, this is, the first one is the theme for this presentation, that you look at emission sources, storage sites, we study transport infrastructure, utilization, and renewables. For the non-technical mapping, it's looking at the stakeholder needs, regulation, climate politics, and funding opportunities. So this was the focus for the first year, and now the project is moving more into the whole value chain, looking at transport solution, how you actually is going to do it, cross-border aspects over the different countries, and SWOT analysis. In the end, it will be a full value chain development, looking at the full economical part, and how this should be done. And we will have one case studies in Baltic and one in Mediterranean area. And the reason for that is that when the project was written, up to now, it has been a lot of focus on UK and Norway especially, and now we want to move it to other areas that is not so developed in Europe, and then that is the choice for these two specific areas, and we will give some results from these areas. But the main focus in this presentation will be on this, what we call regional screening, looking at the emission sources, how we do that, storage sites, transport infrastructure, and utilizations. And I will not talk much about renewable in this presentation. So what do we work with? So, of course, as a first part of the screening phase, it's very important to get an understanding of the biggest emission sources, the amount, share of biomass, location, and type of industry. So this is a picture, a very nice picture actually from the Norcem in Breivik, Norway, with the production of cement. So this is just an example of one of these emitters. We get the data from Capture Map, is owned by Endrava. It's mainly two sources of data. It's this EU emission trading system and the European Pollution Release and Transfer Register. And this is QC'd by Endrava. But during the project, we saw that we also needed to have extra QC for the areas that we're working. So we have QC from CCUS ZEN partners from Denmark, Sweden, Finland, Estonia, Latvia, Lithuania, Poland, and France. And in addition, we saw that we were missing actually input data from Turkey. So this will be the focus on the next presentation after me with Betel, presenting what I did, especially towards capture mapping in Turkey. To the right is a figure showing these plots from Endrava, but we have made our own plots using QGIS that I will show you afterwards. So that was a little bit how we do the mapping of emitters. Another important part is the transport infrastructure. Then we used or did a screening of existing pipelines. We studied transport corridors, distance, capacity, if you can use waterways or ports, railways or roads. Ships is also now coming a lot. This is just an illustration picture from Japan, with the first CO2 transport ship for CCS demonstrated last year by Mitsubishi Shipbuilding. And we know also that Northern Light is planning shipping, so that is of course an important possibility for the infrastructure in addition to pipelines. We have used mapping developed in a project called CO2 loss. It's a SINTEF-led project for logistics by ship, and it's now in phase 3. And that in that project is developed a cost tool to look at how costly is ship transport if you're using ships or barges. In addition, we have used the PSI transparency platform combined with OpenStreetMap, and this is used for pipelines, online pipelines. So then you get maps showing all the pipelines in Europe, and also these transport corridors related to electricity, gas, CO2 if it exists, smart grids, and ship routes. So that is very nice to check if you're interested in transport part. So now we have said a little bit how the emitters and the infrastructure, and the third important part is storage site. We have been focused on in the storage screening on the saline aquifer and depleted reservoir. But we know, of course, that there are also other opportunities for storage. This is a figure by the Norwegian Offshore Directorate in Norway, presenting you have these abandoned hard common fields or depleted reservoirs that can be used for storage. You have shallow saline aquifers. In some areas like Iceland, you can use basalt from volcanic rocks. And also, you can also use producing field, like what we call with this increased oil recovery, but then you don't get it fully 100%. So in this project, we have focused on only on saline aquifer or depleted reservoir, and not including EOR. So how we do it? For the capacity estimate, we use these quite well-known calculation for storage capacity, calculating the volume, the area with the thickness of the structures. You have the net gross ratio of the traps. So you have in percent the net gross. You have the porosity of the reservoir for the trap, and the density of the CO2 at the reservoir condition. And in addition, you have the storage efficiency factor that can be quite field specific and have a lot of uncertainty, I would say. In addition, we have been using this storage readiness level that have been developed by in a previous ACT project called Align with the BGS and quarters. And in this one, you look at, it's a classification system looking at how much data you have and how mature your site is, starting with just first pass with only storage capacity worldwide. And then if you have, in the beginning, you have only level 2, you have identification on theoretical capacity. When I made these slides, I thought most of what we have included is in SRL level 2, but actually I saw that depending on the countries, we have some up in 3 and 4. So you see if it's readiness level 4, you have already validated by desktop studies, and then you have ready. The next phase is this with exploration permit. So we think it's a quite nice way to look at storage readiness level, to look at using this ranking. Then you can easily see how much data you have and how far you have the site have come in the planning. So at SRL 5, you have the starting the exploration permit, and then you have up in storage level 9 with the injection permit. But in this study, most of the sites is from SRL level 2 to 4. The mapping, technical mapping, is built on existing projects. You have an overview here of the main projects like GetSco, GeoCapacity, CO2 Stop, Nordics, Strategy CCUS, and Strategy Pilot that is ongoing now. and we have data from several countries. This is just an example from the Nordics project some years ago from Antonsen from 2014. In that project, we did mapping for the Nordic countries, and you see the main structures included, like the Faluden storage unit in Sweden. You have the Gassum aquifer offshore, and also some on-land traps. And in CCUS, we look at both on-land and offshore storage sites. This is a little bit how it looked like, what we have been included. You look at all the names, where it is, what kind of the porosity, temperature, pressure, everything you need for these capacity estimates. And also the sealing properties, lithology, thickness, where you have the source, where the data come from, and so forth. And then we have the capacity with uncertainty. That's quite important to be aware of. You have the mean, the P90, P40, P10, and so forth, and how this has been calculated. And then some on the project year and the storage readiness level that I think is quite important to include. Also, if you have information about your wells and what if they have been doing modeling, what kind of modeling, and what kind of injection tests, if available. So that was the high-level screening of the storage sites. So to sum up, we look at what kind of reservoir, onshore, offshore, capacity, injectivity, CAPRO properties, and storage readiness level. Below the industry clusters, we have also included the utilization, and we have not been working so much on that, but we are leaning a lot on what had been done previously. So by utilization, we mean that this transformation to using technology and use the CO2 to other business, like chemicals, polymers, building materials, and so forth. And we have been using existing CCU project database from CO2 Value. It's online, and this is built on a lot of existing and upcoming projects, approximately 150, and the big ones is from Scott and Impacts 9. And then you get a mapping of different utilization for Europe, and you can go in and check what exists and where, in which countries you have the different utilization developed. And this is only some examples. So, okay, so now you have had an overall of the methodology, what we have tried to achieve, and now I will give some example from the Baltic and Mediterranean region, what have been done. So we have been, for the Baltic Sea region, we have included work from Denmark, Sweden, Finland, Germany, Estonia, Latvia, Lithuania, Poland, and Baltic. And it has been concentrated in different areas, like the eastern part of the Baltic, Poland and Western Germany, and Denmark and West Sweden. For the Mediterranean, it's Spain, France, Italy, Greece, and Turkey. And you have these three main areas. And we will give you some examples from each of them, I think. In the work package 1, 8 main CCS value chain was selected. 4 in the northern part in Baltic, and 4 in the southern part. So this is just an overview of all of them, not to give too much confusion, but just to say a little bit what we have been working with. So there is a lot of information in this table. So if you what have been selected is that we have these 4 that we think is the most likely one. We have written which countries that is involved. Some of them is several countries, some of them is only one. So this was the start of this 8. And then we mapped total CO2 emission, how many emitters we have, how many clusters, the storage capacity in the region, how long total or year of storage, and then the distance for the transport solutions. So this is really a screening. I will show you a little bit more information of all of them. The map also show, you see the storage capacity is presenting the storage site, like if you look up in the Baltic region, we have this big Falunden unit, and then you have different storage sites marked in brown, and the capacity shown in milliton is shown with different colors. Yes, and one thing to be aware of with this mapping, that these units that we show, or storage sites that we show, is not all that exists. It's a lot more, but this is the one that has open data set that we get, that is easy accessible, and is a first start of the building up such a database. We know there exists a lot of more storage sites, but that have to be included in a data phase or another project. Okay. So to give a more detailed example, if we start up in the Denmark, two value chains have been selected. So the biggest one is the one outside the circle, Baltic 2, involving Germany, Denmark, and Sweden. There you have 8 potential emission clusters and 8 potential storage sites. So you see the storage site marked: Bifrost, Greensand, Ines, Lisa, Jammerbucht, and so forth. The blue, pink, and purple show the emitters. The clusters are emitters, and then we have the yellow ship pipeline marked, or pipelines developed. So this is a CCUS value chain. Baltic 3 shows a smaller one with still 3 countries involved: Germany, Denmark, and Sweden, 4 potential emission clusters, and 3 potential storage sites. So during the project, different value chain have been discussed and screened. So this is really the first screening phase. And after this, the Baltic 2 was chosen to go further in a bigger study. Okay, so this is just showing the name of the clusters, that you have Bremen, Hamburg, and Hanover, that can easily be shipped out from Bremen to these different storage sites. So this is just showing some numbers for the clusters in the different areas, the amount of emission, how much is captured, assuming 90% is captured, and then how much that results in 90 million tons per year for CO2 that can be stored. And you also see the numbers of emitters. And the circles here show the size of the emitter clusters that is larger in Germany and Sweden than in Denmark. Right side. In Denmark, there are several onshore storage and some offshore. So this gives an overview of the 8 storage sites that have been looked at. And they have different volumes for storage from ranging from Lisa, that is quite small, 29, till over 200 for Volden. Yes. And a lot of things during this project, a lot of things has been going on already. We see that so when we started, this structure have been mapped by GEUS, and it have been licenses weren't going on before Christmas, I think, in Denmark, and the 9 industry have been interesting to start with CO2 storage. And who will get these 5 licenses will be announced soon. But you see that many of the structures that is now out for licenses is also the ones that we have been using in our study. So that's quite interesting. You also see green sand and Bifrost. This is CO2 saline aquifers shown in this example or this map. So, and you also see in Norway there is many storage aquifer out for licenses. So it's a lot is happening these days in CO2 storage, I would say. Okay, so that was a little bit about the Danish site, and then in the southern part we have the offshore Spain value chain. There also we had this first screening. Mainly by BRGM, having being in lead, looking at different clusters in Barcelona, Tarragona, Lyon, and Fos-Marcel in the first screening, and then looking at where to store. And this the most what is chosen to go further is this Castellon sandstone that was presented more in Madrid in the CCUS event. This is just a slide that I borrowed from Isalin with maps from the pilot strategy project showing the structure with these sand units. Just offshore Tarragona, 58 kilometers from the shore. So this is one of the selected site that will go further in full techno-economic evaluation. Yes, so the capacity of the site is at least 200 milliton. Maybe more, but this is the one that is the official number from Repsol from that meeting. Okay, so that was a little bit about Denmark, about Spain, and we also have done some work in Italy, doing the same exercise, mapping potential clusters for emitters using this Andrava. You have one in Sicily, like the Prio Gargallo, that is 7.2 million ton. Taranto cluster, very close to storage site, the Branica storage site. It's 12 megaton per year, and the Brindisi is around 6. So it's a very huge number of emission. yearly emission. And the storage capacity is from 340 to 1.3 gigaton. But this is depending on what we use for this storage efficiency that I mentioned for how to calculate the storage capacity for the site. So that's very important to have some feeling on the possibility, and to be really sure you need more simulation like dynamic modeling. What we have been a bit challenged on is this with annual emission, because the amount of emission is very much depending on what kind of industry you have. Like here you have a lot of refineries, cement, power. Not all of them can use CCUS. So we have used, this is Genesis that have come up with a model for how much from the different sectors that can be stored. So this is work in progress, but we assume that, like for chemicals, we assume 35% can be stored with CO2 storage, and the rest would be other methods. Iron and steel, 25%. This is from EAA. Refineries, 50%, and so forth. So we have done made some assumption how much can be used for CCUS. And then using this for the Italian site, using this that we for each cluster have the total CO2 emission, and then use this % in reduction depending on CCUS, you get a much more realistic number how much CO2 emission can be or should be available for CO2 storage. So then it be a little bit less than 50% that can be stored. Yes. So a little bit about the challenge. I think this with the data is a big challenge, that you need to be able to do the screening. You need access to geological data, you need access to interpretations and well data and so forth. And that is a big step, or you need to have open data to be able to do a lot of this screening. And also to get it further, you need much more detailed analysis, like dynamic modeling to mature the site, but also for the whole value chain, you need more analysis, and that in CCUS ZEN that is taking further in work package 3 and 4. So I will really encourage you to listen to the webinars during the autumn, taking this work process further and going from screening to really selecting sites and really do detailed analysis. Another challenge was this with capture, what to report, because we know that some is going, you have some biogenetic emissions. So the project decided to map the biogenetic emissions and have that separated from this fossil CO2 emission, if possible. So that was done, but I'm not focused on that. Yeah, and now in this presentation, I've talked a lot about the storage part, but my colleague in Turkey, Bartel, will talk a bit more on how to map the capture. So that will be handled in the next presentation. So just to finalize, because there are some hope here, I think. Yes, on Friday I listened to another webinar by Anka Petre from the European Commission, and there is proposed and there will come obligation that the member states should publish data and information about CO2 storage. So I hope that can help in future screening to have even more data to available. Thank you very much. And now, and here is some references. You can meet us at GHGT. And you see here, it's a lot of co-authors on everything. So it's really a big effort on collaboration. And you see here, this is the 2 reports that have been published from Work Package 1, and another one will come soon. Thank you very much. Please.
Yes, thank you so much, Anne. Shall I also share my screen? Okay. So good afternoon, everyone. Hopefully you can see the screen, right? Can you please confirm that?
Yes, that's we can see that too.
Okay, cool. Again, good afternoon, everyone. I'm very happy to be with all of you today, actually. And as Anna mentioned, I will just be mentioning about this mainly technical mapping of CO2 emission sources in Turkey. And team members are also written in here. So we have worked as METU Petroleum Research Center. So we have mainly discussed about that, but regarding the Turkey case, we can say that actually for the rest of the Baltic countries and for the rest of the Mediterranean countries, we have used this Andrava capture map, which was mainly indicating the facility-based emission data, CO2 emission data. And this data source was mainly coming from this ETS, emission trade system, and also EPRTR. So that for the rest of the countries it was okay, but for Turkey case, at least for now, the ETS mechanism is not active. So we don't have the facility-based CO2 emission data. For that purpose, we require to limit the sectors indeed at first, because we were trying to calculate each facility emission by ourselves by using some empirical relationships and recommended methods. So that we just use certain leading industries, let me say, which was including this refineries and petrochemical industry, power plants, iron and steel, and cement factories. And you see the data source and methodology. Indeed, in Turkey, we mainly have 5 refineries in total and 1 petrochemical industry. And it was more convenient or much easier to find data of that from the public reports of Tüpraş, which is also the networking partner of these projects, and SOCAR. So it was an open and public data for the yearly emission. But for the rest, such as power plants, we require to calculate the emissions based on the proposed emission factors by Ministry of Energy and Natural Resources Turkey. And for the iron and steel and cement factories, we mainly depended our calculations on the IPCC methods, actually. So regarding these sectors, I will just try to give a very brief summary of each, actually, whatever we have done in general. So as I told before, we mainly have 5 different actually refineries. You see the locations. One is Batman in southeastern part and in the mid part of Turkey, and then in mainly the Marmara and Aegean region of Turkey includes. And these 4 refineries are owned by Tüpraş, Turkey Petroleum Refineries in Turkey. And we also have 1 more refinery, which is owned by SOCAR Turkey. And it is very close to the Izmir region, actually, this Izmir Tüpraş refinery factory. And we only have 1 petrochemical industry, integrated petrochemical industry in Turkey, which is owned by SOCAR as well. So on the map, you can see the operational capacity per year of each refinery and petrochemical industry, and also the emissions, yearly emissions, actually. I can say that in total, we have almost 10 million tons coming from these refineries and petrochemical industry in Turkey. And regarding power plants, we were not that lucky to find open source. And we just tried to focus on the factories which have more than 100 kiloton per year emission, because in the project we have done that for the rest of the countries as well. So accordingly, we mainly evaluated like 108 power plants, and almost half of that were working with the lignite and hard coal. I am telling that because these emission factors were mainly related with the type of fuel. If it is more dangerous and more dirty, it was having much emission factor accordingly. And the rest of the power plants were mainly fueled by natural gas, exported coal, and fuel oil, actually. And according to that, we have used certain factors. I'll be showing that based on the used fuel. And also we had the installed capacity of each, let me say, factory. That was the problem because actually we have behaved like most, or we have thought that the most pessimist scenario, let me say, because we try to use like 100% efficiency. The full installed power capacity have been used. So that it was the main assumption that we have done. So this is the most case that we have calculated the power sector. So this was not the real CO2 emissions, but the most or the highest amount of CO2 emissions coming from the power sector. So these are the CO2 emission factors recommended or proposed. As you can see, of course, for the lignite and hard coal, we have the higher emission factors, and for the rest, for natural gas, for example, we have less amount of emission factors. And as an example, we have a kind of thermal power plant, and I will be just showing the data. We have collected data in that sense because actually for the other type of countries, that we have collected data from Andrava, we're mainly including facility, company, all the coordinates, and the rest of the data. So we just try to collect the data in the same manner. So you see that the type of fuel is lignite, so we have used the according or corresponding emission factor, and we have the installed capacity. Normally installed capacities are given in megawatts, so while we return back to that in megawatt hour, we have again assumed the most pessimist case as like we use all hours in year actually. So this 8,760 hours per year was the second assumption. So accordingly, around 6 million ton per year was just coming from the Soma-Kolin thermal power plant in an Aegean region, I can say. So the rest of the companies were being processed in the same manner. So regarding the iron and steel industry, you see the map. This is the steel map of Turkey, and you see different colors written, the written words actually, and also you see the different colored symbols. Well, these symbols actually represent the different colors of them represents the capacities. So for example, if you see the red one, it means that we have more than 2 million actually capacity. So if you see the green one, it has the least capacity. So on the other hand, if you see the names in different colors, the different names implies different methods used in the production of iron and steel actually. So mainly I can say that we have 3 integrated iron and steel production facility in Turkey, which use this basic oxygen furnace. And the rest of the ones are mainly using the electrical arc furnace, and very, very few of them are using the induction furnace. So mainly 3 technologies are being used in Turkey to produce iron and steel. And why we are separating in that manner as well, because they use different fuels in the method, so that, for example, BOFs release much more CO2 than the EAF, let me say, furnaces. So accordingly, IPCC proposes a kind of tier 1 method that we have used based on the data in our hands. So you see that emissions, CO2 emissions are mainly related with the technique used and the emission factor corresponding to that specific technique actually. So if the company is using BOF, we have the amount of how much crude steel production is occurring from there, and emission factor is coming from IPCC recommended value as 1.46 tons of CO2 per tons of steel produced. And if the company use the EAF instead of BOF, a much smaller emission factor of 0.08 tons of CO2 per tons of steel produced have been used actually. And there is a very simple, again, one of the biggest, we have İsdemir, Kardemir, and Erdemir as the BOFs. They emit the largest amount of, let me say, CO2, so that these are the information and according calculations made accordingly, actually. And finally, I will be talking about the cement industry. So that, again, we have depended our calculations on IPCC recommended techniques. Indeed, IPCC recommends or proposes different methods, like 4 or 5 different methods. But based on the availability of input data, we just selected our methodology accordingly. So that either tier 1 or tier 2 methods have been used. According to what? Well, mainly we have the crude steel production from these companies, and based on that, we either use the steel production, yearly steel production data, and indirectly calculated the clinker production. Clinker is the byproduct, by the way, and IPCC recommends calculating the CO2 emissions based on the clinker use, so that accordingly, if we only have the steel production data for the company, we just use that cement production to calculate the actually clinker production by using certain factors. And if we directly have the clinker production data of the company, somehow we had, for some companies actually, we chosen the tier 2 method. In other words, let me show the methodologies proposed. So as you can see, for the IPCC tier 1 method, you have a kind of cement production type of cement, and we only have one type of cement used, so that we only have one type in here, so that multiplied by the clinker fraction of this cement. So this is the default value of that is by IPCC is 65%. So we just have the steel cement production, and 65% of that will be the clinker production. And in the equation you have the IM and EX. They are imported and exported cement. Since they are not included in the calculation, so they are being taken as 0. And EFCLC is the emission factor for clinker in the particular cement, so that the corrected value for that is 0.52. Tier 2 is simpler, of course, if you have direct clinker production data rather than cement production data. So you directly use that clinker amount in tons, and then you have the, again, this 0.52 overall, 0.51, and multiplied by correction factor, which will make 0.52. So that accordingly we have calculated the all the cement factories in Turkey, and this is again from Aegean region. I show a case about the Soma cement factory, and we have used the tier 1 because that we only had the cement production data, so that accordingly we have found almost 0.7 million tons of annual CO2 emissions from only one company. So I will not go into detail after this part because this was the main difficulty for us to collect data for Turkey case. But all in all, the overall estimation of the Turkey's CO2 emissions were still very close to whatever the statistical institution declared for 2021. So it was not too far away from there, even if we have made some assumptions in our calculations. And in the end, we have seen that the main CO2 emissions in Turkey are mainly coming from the Marmara and Aegean region. So that we try to choose our emitter clusters mainly from that area. So you see the emissions in terms of kiloton per year, and the darker colors represent the higher amounts, of course. So based on these cases, we mainly chosen 2 clusters in the Aegean region, total of which makes 40 million ton of CO2 emission per year, which is high amount actually. And accordingly, you see the distribution of the contribution of different sectors, and we mainly have the power industry and refineries, iron and steel and chemicals actually. For Soma cluster, we mainly have the power and cement industry accordingly. So regarding the value chain proposed, indeed, we have storage sites in Turkey, but they are mainly, the storage facilities are mainly working as enhanced oil recovery case because the regulations only exist about that. So for that reason, we try to choose a kind of Greece case to store our CO2 emissions, which is very close to the Aegean region actually, which can be transported through the ships, let me say. And accordingly, there are 2 different storage sites have been discussed. One is Prinos Basin, which is mainly offshore deep saline aquifer, with a very huge amount of capacity, 1,000 million tons of capacity. And the other one was Selanik Basin, which has less capacity compared with Prinos. And indeed, it has onshore and offshore storage sites. So accordingly, 4 different cases have been discussed, but the best one has been chosen as bringing everything from Soma cluster to İzmir Aliağa cluster first through the pipelines, and then carry all these emissions of 40 million tons to the Prinos offshore basin. So in that sense, we have 40 million ton per year, 1,000 million tons of capacity, so 25 years, which is a feasible case actually for CO2 storage, has been supplied by that. So regarding that, let me say the value chain, you see this is named by Mediterranean 1, and the emission clusters in there includes 2 different clusters, mainly Aliağa and Soma. And we firstly use the pipelines of 120 kilometers and then bring everything to Prinos site by ships to store. Of course, there are so many complexities regarding that value chain as well, both technical and non-technical, such as unavailability of infrastructures, transportation and storage yet, and some regulations actually, because we are gonna inject in offshore. So there are also some social and regulatory part of that. But still, this was one of the Mediterranean proposed value chains for us, and of course, still under the evaluation with all other value chains. So hopefully you will be able to hear about them in the next webinars. So since Anna has already mentioned, I will not take your time about the further reading part. And I can just ask if you have any questions. We will be glad to answer them, actually. Thank you very much for your patience.
Thank you very much, Betul, and thank you, Anna, for both of you for your presentations. We can now begin with the Q&A. A reminder that if you do want to submit your, or if you want to make a question and speak it, I'll just enable microphones for attendees now. Please, if you do ask a question, use the hand raising function and only unmute when you're asking a question, just as a courtesy to everybody else. Anna, there was one question that came through the chat during your presentation that says, will the CO2 specifications needed for injection be the same for all these injection sites, or will they have their own CO2 specs?
Yeah, thank you very much for the question. Yeah, that's probably an economic question also, and also depending on the source. I think you will, I think the industry will prefer that in the end that there will come a standard, but till now, okay, Northern Light have set a certain standard, but that is I think because of they want to have this ship transport. But I think the specification can vary depending on what kind of site you have, as far as I know. I think it's more on the transport that will have influence on what specification you should use. Yeah. You are muted. Yeah.
Richard, I don't know if you were referring to me, but yeah, we cannot hear you, Richard.
Sorry, I was muted. Yes, Guillermo.
Okay, I read your lips. I thought you were saying Guillermo, so I assumed it was me. Thank you for the presentations. I'm Guillermo Martinez from the JRC. My question is because I heard for the Turkish case, you were assuming, you said the worst case scenario, assuming that the plants are operating for 100% capacity factor. And my question is that different in Endrava for the non-Turkish case, or does Endrava assume also the installed capacity? I don't think Endrava accounts for the actual operational hours, or does it?
Yeah, actually, ANRAVA includes the ETS data and EPRTR data. So these are the real emissions. Actually, they don't make any calculations, but rather they get the data from the ETS and EPRTR, so that they have the exact data. So that it's not maybe 100%, but whatever for per month, per year, they use that one actually. Yeah.
Okay. Thank you.
Thank you very much for the question.
We have another 5 minutes or so for questions. So please, again, use the hand raising function, or please feel free to submit your questions on the Q&A. Okay, we have a hand raised.
Yeah.
Go ahead.
Hi, I'm Shamim Mehder. I have a question from Anna. You mentioned that the biggest challenge is the data collection. Can you hear me? Yes.
Yes.
Yeah.
Yes, data collection, geological data from different countries, and of course their geological sites. So is there any like policies or regulations are in place or being made to make such collaborations among governments to share this kind of data? Are you aware, or?
Yeah, it was what I mentioned in the end, that because I think that have been a bit, we are quite spoiled in Norway, because in Norway you have this, the offshore directorate have this regulation that you have to, all companies have to share the data in this, that everything get shared after 2 years, more or less.
Yes.
So that it's so and that also is very good for the academic, actually in the whole world, I would say.
Yeah.
But what has come now is this from the EU. But I don't know how that will be in practice. I can show you once more that you can. Oh, I put in, yeah, that it's said that now I shared in a very strange way. Sure. Just want to go to the.
It's just to understand if the IEA or IPCC or any other authorities, they are helping to make such kind of agreements among the different players.
Yeah, because now I saw that the plan that it should be. Just 1 second, sure. That one. That all the members that have to publish data for CO2 storage.
Yeah.
And I saw that also in the next slide that I didn't include here. It was also because we had a discussion if that was only the geological society that have to share, but we saw that also the oil and gas industry had to share data now, or that is coming now from June or next month.
Okay.
So that if that happened, that would be fantastic, but I'm not sure how it will be in practice.
Yeah.
What is also possible to that is that there is a Sinta have this CO2 data share, and there is a lot of data, but especially from the North Sea, that is given from oil companies that can be used by everyone, that is open accessible. So there you have 3D data set to test methodology.
Okay.
And yeah, so if other countries want to use that, I think that will be no problem to share data open in that forum.
Yeah, sure.
Yes.
Thank you very much.
Mm-hmm.
Thank you very much, and thanks everyone for joining today. Thank you, Anna, and thank you, Batul, for your contributions and your presentations today. Very informative. I'm popping onto the chat again the address for the events page of our website. A reminder that the third webinar in the series is going to be in September time. The date will be confirmed very, very soon. So please keep an eye on the website. I encourage you to follow the project also on our X, formerly Twitter account at CCUS ZEN, and also you can find us on LinkedIn. So once again, on behalf of the project, the presenters, thank you very much, and we'll see you again soon. The recording will be available on the website in the next couple of days. Thanks again.
Thank you so much.
Thank you very much. And this publication is on GHGT. I forgot to say that. Thank you.
Thank you. Thank you so much.
Thank you.